and then I'll get started with my talk. Okay, so design of JuMP and MathProgBase. What I'd like to accomplish is explain a lot of things about JuMP, maybe not everything. Some of the details about how JuMP evolved, what were the decisions that we had to make, why things are the way they are, what are the things that that are the way they are for a good reason, what are the things that are the way they are for maybe not a great reason. And this should be a good starting point for the rest of the discussion, so we can have at least start on the same page and have a good idea of what the key points of the internals and what we can do to improve them if we need to. So Juan Pablo mentioned this a little bit, but when you understand JuMP, it's important to think about what were our motivations in creating JuMP. And our priorities were first to design something that's modern, fits in with modern tools, modular. You can put a model inside of a piece of a model inside of a function, compose it with other pieces. That's very important. Being able to embed modeling inside of a larger problem, like a simulation, visualization, all of that ought to be easy to do. What we'd also like to do is, since we use mixed integer programming solvers, we'd like to interact with them while they're running using callbacks, feed in heuristics, lazy constraints, the usual business that you do when you're interacting with the MIP solver. But this is something that historically you had to code to the solver-specific API, and if you wanted performance, you'd probably write it in C++. And also being able to extend the modeling interface to specialized problem classes. Basically, the commercial tools were not designed to be extended. People have unfortunately spent some time trying to extend the commercial tools, and it's a lot of hacking. People have made people have reverse engineered AMPL syntax and written custom parsers for AMPL so that they can build an extension on top of it, and that's definitely not a fun thing to do. I would say that the commercial tools are some of them are not modern, some of them are kind of modern. They're not easy to embed. You either they're mostly standalone. You have to either communicate through files, use some API that have to match up with, you have to start understanding the translate between the data of the model with the data of your problem. It's not a very natural fit, at least from what I've seen. And on the other hand, we have open source tools. At least when we started working on JuMP in 2012, we had open source tools that you could call them modern, easy to embed, modular, possibly extensible, but these tools were basically slow. If you wanted to solve a linear programming problem in a loop, add a new constraint, solve an LP, add a constraint, solve it again in a loop 1,000 times, you would run into a lot of overhead by using these Python or MATLAB-based tools. So you end up having to drop down to C++, and, well, that was not fun. So Julia came along. I think in February 2012, I was working at Argonne National Lab, actually on large-scale methods for linear programming. And I believe I saw this blog post possibly on Slashdot, and started playing around with Julia. I implemented a prototype of the simplex method in Julia and got pretty decent performance. and that convinced me of the performance aspects of Julia, and that was even before I knew about macros, about all the fancy stuff, but it was good enough to get me started. So in October 2012, this was first year of my PhD. Ian and I sat down and were playing around and wanted to see if we could make a linear programming modeling language. You'll notice there's some typos even in the comments, but this is the actual code that we had starting out. We called it JuLP. It was Julia for linear programming. And so the name JuLP has some influence from Pulp, which is another Python-based modeling language, which Ian had worked on before he came to MIT. So it was JuLP, and with JuLP, the first implementation question, if you're writing a modeling language for linear programming, well, your really first big question is how do you capture linear expressions inside of a programming language? That's a pretty fundamental design decision. So I want to, we presented JuLP at the first Julia, it was probably the first Julia meetup in winter 2013. The video is still on YouTube if you want to watch it for historical interest. And you can see back then we had already made our core decision. We want to use macros to avoid issues, whatever that means, with operator overloading. And we had a very different syntax at that time, but it was basically we had a macro that could take apart an expression and turn it into a data structure which represented a linear expression. And then, so I want to actually go into more of the details of what are these performance trade-offs. I gave a lecture in Alan Edelman's class back in the fall. I mocked up some of the basic ideas here. So let me just walk through this a bit. We can define a variable as, so this is, if you haven't seen Julia.6, this is the new name for a immutable type struct. We can define a variable as a something that holds an index. Let's call it like a column index. We're an LP, so we have a column. We have columns and rows. And then, well, in each row we have some affine expression which defines the linear constraint. And we need some data structure to represent the affine expression. And by affine expression, I just mean a data structure that stores the coefficients, variables, and some constant offset. So you could define an affine expression as just a list of these variables, their coefficients, and then the offset. Is the code big enough for everyone to see? Yeah. Okay, so the first thing you would think about is, well, I have this affine expression. I can define addition of two affine expressions just by concatenating the variables, coefficients, and adding the offsets together. I can define multiplication between a number and a variable to give you a new affine expression. I can define an empty affine expression, and this is about all you need to implement operator overloading in Julia. So then what you could think about doing is using, well, a pretty natural syntax. Write down a generator statement. You can sum over a coefficient, let's say I to the power 1.5 times a variable with column for column I. So this expression will build up an affine expression data structure just by these operator overloading rules. And this generator statement, you could pick it apart and write a similar loop, which is, if you're using C++, your loop would probably look like this. You can start with an empty affine expression, loop over 1 to n, and just add to it, append to it coefficient times a variable. This product will be an affine expression which is created from the multiplication overload. This plus equals, in Julia, plus equals is entirely equivalent to that. So plus equals is not fancy. It's just it's the result of the right-hand side added to the left-hand side. Okay, so this is kind of the very straightforward operator overloading approach. If instead you were serious, like super serious about performance, I don't want modeling languages, I'm going to code my matrix in C++. What you would probably do if you're writing a matrix generator is write a loop, and you would directly build to this data structure by appending to the variables and appending to the coefficients. This is maybe what a matrix generator would look like for this problem. So those are two different ways that you could build up this data structure. One, I'd say the first example is a pretty nice syntax. That's almost a modeling language. The second syntax, this would be called a modeling language in C++. Sure. This, if you're building sparse matrix directly, your code would look something like that. And there's one more way that you could collect these expressions, which is instead of here, whenever we whenever we have an addition of an affine expression, we actually create a whole we create new arrays. This is actually, so this operation is kind of an expensive operation. It's linear in the size of the two expressions because you need to create a new array that has the length of the components of each original expression. So this is kind of an expensive operation. You could be lazy about addition, and you could define a graph data structure, expression graph data structure, where you keep a list of the operations that happen. So your basic element of the structure would be a node. The node could tell you which operation this belongs to. So it could be a constant, it could be a variable, it could be multiplication, it could be addition. The node could have children, and let's just say the node has some metadata. So if it's a constant, the metadata will be the value of the constant. If it's a variable, then the metadata will be the index of the variable. And I've typed this concretely, so there's no performance hit for abstract types in Julia. So this is a concrete type. It'll be stored efficiently. And what you can do is, okay, so if we get things into this form, we can define a constructor to turn a variable into a node of this expression graph. And I'll just create a node. It's a variable node, and plug in the index there. We can have a constructor to turn a constant into a node of this graph. And then we can define multiplication of two of these nodes as creating a new node that has multiply and has a reference to the two children as elements of the operation, and same thing for addition. So this is another way that you could represent this expression. And I'm going to take I wrote a little function here that takes a graph with a very particular, the graph corresponding to the structure that we're about to build. So this is not a general function, but if the graph happens to correspond to this expression that we're about to construct, then this function will take this graph and turn it into a concrete affine expression structure. So you basically, you can either recursively walk the graph, or there are more efficient ways to do it, but I'd say this is a reasonable thing to do for this particular structure. So if it's multiplication, well, you pull out you know that a multiplication is always going to be a constant times a variable, so you pick those metadata and the variable out and push it into the affine expression. So this will turn your graph data structure into this affine expression. And then our modeling language here would look like the syntax. To make it concrete, we can to build up this graph, we can do sum over, turn the constant into a node, turn the variable into a node, and sum over that. The G will be our graph structure, and then we can convert that graph into an affine expression after we've built the whole thing. So those are three different ways that you could. So I would also call this is also a modeling language. You can make it look as nice as this generator syntax here. And the question is, well, which way should we? How should we actually go about building these data structures? So question for the audience: if you use the generator or the loop, so they're both using operator overloads based on concatenating affine expressions, what's the complexity of building your final affine expression object in terms of n? Yep.
Quadratic?
Yes. So it's quadratic because every time you add something together, you have to do an operation that costs as much as the length of the things that you're adding together. If you're doing if you're manually building up the array, this is obviously linear in the size of the array. And same thing with the graph. You can structure it so that it's linear in the number of operations in the graph to extract the data structure. So in this case, there's an algorithmic benefit to being lazy instead of trying to build up affine expressions for the first time that you possibly could. So which way did we choose in JuMP, if you know about JuMP internals?
The linear way? The manual?
Yeah, so we do manual, but it doesn't look like that. Let me show you some benchmarks. Let's see if I can.
Miles, can I ask you a quick question?
Yep.
So one advantage of the quadratic kind of version is that it's immutable, right? Every time you're getting a new object that's like totally doesn't touch the previous ones. So I guess that's like a trade-off that you have to make, like performance versus immutable.
Yes, but if we had chosen the quadratic way, we couldn't be fast.
Yeah.
Like, so that was a bit of a. That was the first thing we did. We implemented very basic operator overloading and found it to be slow, both because it was quadratic and because at the time Julia's garbage collector was not good at all. It's improved since then. And whenever you had an operation, you would create a few new objects, and it's a lot of work. Let's see. Okay, benchmark. So this is nice benchmark macro, which will tell us how long a single call takes. So if you use the generator statement with n equals 100, it takes 30 microseconds, or let's look at the minimum time, 30 microseconds. If you turn into 1,000, it will not be 10 times. It will be closer to 100 times slower than 10 times slower. So we went from 30 microseconds to a millisecond. Take the loop, that'll be same as the generator. Take the manual approach, 7 microseconds, multiply by 10, and it should be around 70 microseconds. And if you take the graph approach, so this is also linear, but there's a lot more overhead involved. You're creating these objects. You have to walk through the graph later on. So for the same size graph, you it takes 30 microseconds instead of 7. But if you multiply it by 10, it will grow linearly with the size of the graph. Yeah, so it grows linearly, but there's a substantial constant factor between 70 and 300. So if it could possibly be brought down a little bit, but there's a decent constant factor in there. So the way that we actually chose to go about capturing linear expressions was something you could only really do in Julia. Something with macros is kind of crazy to do otherwise, but we chose the manual approach. But when you write the code, it doesn't look like that. We have macros that transform the expressions into the manual code. So this is a little bit of a macro. Here's a function that would take an expression object like this generator statement, pick apart the pieces, and generate the code that basically looks like what you would write down manually. And then you can call it you can call it like this. You put a macro in front, write down the nice algebraic expression, and this should work. Uh-oh. And not defined. Okay, this is the one piece I didn't test recently, but you can trust me. It basically uses the manual. It generates code that's identical to this manual construction, so it'll be just as fast.
Is there any overhead?
For that particular case, no. You can look at the code that it generates, and it's the same thing.
But what's the overhead of generating the?
That's a compile time overhead. So in Julia we tend to separate that out because when you compile the function, you have to pay some cost to compile it. But that happens once, so as soon as you call the function more than once, that cost gets amortized out. So I would say it's not substantial.
Okay. But if you're building, so you're building it once, compared, let's say, to gas. I mean, they're thinking on the test, did you include that before on the test against AMPL?
On our more recent benchmarks, the way we timed it was we pressed enter, and waited until it generated the model, which it does include the
and it was so comparable to Apple.
Yeah.
So it's something that you don't really pay for that. So if you're just doing it only once, you don't really pay much for it.
The macros,
but then you would get a lot if you actually run it more than once, which I guess is the point of doing it in Julia. You would get a bit.
But there's also compilation time for any function in Julia, so right. It's not. I don't think it'd be much more. I don't think the macro part itself introduces too much because we're not doing something that's too complicated there.
Right. So it's the same. But even that compilation time with the function ends up being competitive with Apple.
Yes, not for tiny models because there's a fixed cost.
But for big ones where it was like so in one big model you wouldn't see a huge penalty.
Right.
I can comment on this. So in the code base that I run, the first time we run our model, it's about 4 seconds. And then for a model, let's say, is less than 1 second. And then after that, it's less than 1 second. So that's a pretty big set of functions, I think.
Yeah. And there's...
It's like from quick to instant.
Yeah.
So right now, JuMP is not fully precompiled. So not everything in JuMP is precompiled. We could do some more work to cut that down. We haven't looked at that recently. But you could probably shave off some time just by making sure all JuMP and the core packages are actually fully precompiled. Okay, so we made this choice, and this choice has kind of set us on a path. So as a consequence of using macros in this way, I think it's fair to say that JuMP is fast. So we did achieve good performance. We do have operator overloads implemented, and people sometimes write down models that look like this loop because that's how they're used to building the models. So in that case, we print a performance warning saying this is probably not what you want to do, and that warning has seemed to be successful because we haven't gotten complaints about slow model generation since then. But prior to that, people would send us models and they were slow, and it was probably because it looked like that. And as another consequence, if you use JuMP early on, you would know that you cannot write down, you had to write down a coefficient times a variable. The coefficient had to be on the left, and the variable had to be on the right. And that's because when we're doing this inside the macro, with the plain macro, you don't know the types of objects. So here we're picking things apart, and we know that whatever's on the left of the multiplication is a number, so we can push it into the coefficients. Whatever's on the right is a variable, so we push it into the list of variables. And we needed that positional information to be able to do that because the macro doesn't have type information. And so that was an interesting restriction until JuMP 0.7. But it did get us a performance. So our first performance results that we presented were 2013. Here we're just building up a model, writing it out to an LP or MPS file, and we compare the timing, write the model, including the file writing time, to ample gams, Groby under C++, Pulp under PyPy, and Pyomo under standard Python. And we could see that we're basically in the same league as ample and Groby C++. And once you go into Pulp, this is still accelerated Python under PyPy at that time. Pyomo was not accelerated because it didn't run under PyPy. But as soon as you go from the commercial tools to the Python-based tools, there's a huge gap there. So I'd say we were able to close that performance gap. So while we were running these benchmarks, if you looked at our file writers for some reason, you'd notice that right now they don't. They have an option. I think MPS doesn't have an option. LP recently gained an option to write down the variable names into the file. And the reason why we didn't use names is because they were kind of slow in the benchmarks, and especially with there was garbage collection overhead by having a string object associated with every variable in the model. So we didn't do that. And since we didn't want a string object associated with every variable in the model, what we implemented was a lazy naming scheme where if you declare a set of variables from x from 1 to n, it only creates the string objects on the first time that you ask for the names. So that was a little hack we did. It allowed us to be fast when all you're doing is generating the model, writing it to file, and you don't really care about the names. But I don't know if that's still a good reason to not write the names. So if you want to make a pull request to update our MPS writer, that'd be welcome. And we could also possibly reconsider this lazy naming scheme. We haven't done the benchmarks. So what led us to this were benchmarks from 2013. So it could be worth rerunning this and see if there's still an overhead to avoiding attaching a string to every variable. Okay, so after we had after we had basically an LP modeling language, Joey joined in 2013, and I think his first contribution to JuMP was quadratic constraints. And this is kind of problematic for the macro approach that we took. And at the time that we added quadratic constraints, we used plain operator overloading for quite a while and didn't allow quadratic expressions inside the macros. And you can see some traces of this. For example, the expression, if you create a collection of expressions, we actually still only allow you to create a collection of linear expressions for some reason. We'll probably look at removing that restriction, but that's kind of a trace of this. And what enabled us to extend the macros to quadratic expressions were these things called generated functions. So generated functions is a fancy technique in Julia that will generate the code for a function once you know the set of input types. So you can kind of intercept the compiler when it wants to call a function. The compiler gives you a list of the input types. You generate the code for the function, and then the function is run like normal. And so these generated functions, because at compile time we don't know what's a variable and what's a coefficient, but as soon as you call a function, you have the variable types. So by using stage functions, we were able to fix the issue with coefficient times variable, variable times coefficient, and it also allowed us to do a reasonable approach to putting quadratic expressions in the macros. But I would say it's still kind of messy. So we have this generated function, which will, given the set of inputs to the function, it will generate the right expression call, and it will put things, try to pick apart the coefficients and the variables so that we know which coefficients, where to throw the coefficients and where to throw the variables. So this is a bit of why the macro code is 600 or so lines of code, which is actually not too bad, but it could be better.
How?
So what we're basically doing is implementing a compiler in an ad hoc way. The better approach would be to take what we get from macro is the expression that people wrote, the user wrote down. We get the expression. We don't get any type information. If you use generated functions, right now we use generated functions in kind of an ad hoc way, but there's a way to use them to essentially you would get the expression and the type of all the objects together, and once you have an expression graph with actually the types of the objects, you can decide what to do with it and generate the right code. But we don't do a proper job of that.
But it's possible in that with Julia.
Yeah, and some of that goes into CXX, the C++ interface, with Julia's C++ interface, which does some crazy. You can call C++ inside of Julia, and they need this similar thing where you have an expression graph and the types of everything, and then they can decide which code to generate. So if you were going to rewrite the macros from scratch, you'd probably think about using that approach. We hacked things together, but it's ended up being good enough for quadratic terms. So here's our second set of benchmarks, and these are quadratic models with quadratic terms in them. This is model generation time. So this is actually from when we press enter to the time that Gurobi reports the problem dimension. So we'll say that's the time it took to generate the model and hand it off to Gurobi. And for the smallest model, there is some fixed cost that we're paying, but as the model scales up, we're basically in the same league as the commercial tools. And as soon as you go into Pyomo, CVX, YALMIP, there's a huge performance gap there. So even for like our smallest model here, CVX was not able to generate the model in less than 600 seconds, while it took these commercial tools less than 1 second. Okay, so that's how I'd say that describes how we create the objects that represent linear and quadratic expressions, and that's a big piece of JuMP. So once we have the expressions in a nice data structure, what do we do with them? So what does JuMP really do? I like to say that it provides a nice interface to MathProgBase. So once you've collected the expressions in a nice data structure, you have a quadratic constraints, quadratic objective. You have everything you need to write it as a quadratic programming problems. So once it's in the kind of matrix form, we hand it off to this abstraction layer called MathProgBase. And the reason for that, the reason why we choose to hand it off to MathProgBase and not really do so much work at all in JuMP. All we do is kind of collect the expressions, but we try our hardest to avoid doing any transformations of the original data. And that's basically to make our job easier, keep JuMP lightweight. It's very fast. We have a simple job. We're just generating matrices. And we hand off thinking about the transformations to the solvers. You could think about where's the best place to put transformations. I don't know what the answer is. It seems to be that nobody wants to be responsible for transforming a problem, because solvers, if you're writing a solver, you want to say, well, I assume the user has put it into a nice form before it gets to me. And if you're writing a modeling language, you should say, well, the user has put it in a nice form before it gets to the modeling language, or maybe the solver should be responsible for transforming it. I'm just giving you what the user wrote down. It's not my job to transform it. So I don't know what the answer to that is, but since we're writing a modeling language, we'll put off the responsibility to someone else. Okay, so MathProgBase. It started out as an interface to LP solvers, so as JuMP started out as a LP modeling language. Kind of historical note, Julia 0.1 came with GLPK built in. It was, for some reason, GLPK was distributed with Julia because they solved LPs. Wait, that can't be right. I was going to say, they did solve LPs for resolving dependencies in packages, but Julia didn't have packages at that time. Okay, I need to look at that. But Julia did come with GLPK built in. Once we kind of took responsibility for that, Carlo Baldassi was involved with a GLPK interface. We kind of, once we had a standard form for that, that left base Julia. Another thing, MathProgBase is called MathProgBase because for a short period of time, for I think a couple months, JuMP was called MathProg. So if you've ever submitted a package to metadata, there's always some bike chatting on, is this a good name for the package? And for some reason, Viral Shah thought that JuMP was not a good name, so it should be MathProg because that's more clear about what it does. Then we discovered GNU MathProg, which is not a good, which is GLPK's version of Ample. So that was not a good name collision, so we named it to JuMP. So after it was MathProg for a while. So after we had LP, we tacked on integer variables, SOS, special order set constraints, callbacks to interact with solvers, nonlinear optimization, conic optimization. So this all got thrown together in a single abstraction layer. And about a year and a half ago, it kind of got to a confusing state where we have all these available functions, but we don't even know what. I have a solver. Is it a conic solver? Is it a nonlinear solver? Is it a QP solver? We didn't even have a good way to figure that out. So we split the interface into LP, QP, which is kind of covers traditional LP, QP MIP solvers, conic interface, and the nonlinear derivative-based interface. So now those are separate interfaces. And this afternoon we're going to talk a bit more of a proposal for another reorganization, which will affect everything. But I'd say we haven't really done a complete job of answering the question which solvers support what. So splitting into these three interfaces managed the situation for a while, but we can do some improvements, and we also want to generalize the existing interfaces so that we can communicate more general types of constraints to solvers. Okay, so what goes into designing MathProgBase? Well, there's a trade-off between keeping the API simple. Different solvers have different ways of doing things. In MathProgBase, we try to keep MathProgBase simple so that we don't have to do too much work in wrapping the solvers. But we also try to not have multiple ways of accomplishing the same thing in MathProgBase. So there's an issue of when you create a variable, should you specify the category of the variable, like integer or continuous, when you create the variable, or should you specify the category of the variable after the fact with a separate call? And some solvers want the category of the variable when you create the variable. Some solvers want the category of the variable after the fact. And we decided to do this. We started out with the second approach, and we're staying with that approach because we don't want multiple ways to do the same thing, because then you multiply all the different interfaces that the solver wrappers need to support. And since JuMP is also playing an unusual game where it's very unusual for a modeling language to support in-memory modification to models. So when you solve a LP, very few modeling languages will keep the solver in memory so that you can modify it, add constraints, tweak things later on. And that condition, to do that, we would like to keep JuMP's concept of a model similar to the solver's in-memory model, so we don't have to, so that modifying things is simpler. And you can compare this with modeling languages, which just write out the problem to file, hand it off to the solver, get the solution back. And if you want to solve a different problem, we write out a whole new problem to a file, send it out, get the solution back, which is very different. But if you're so that has a big effect on what we choose to do in JuMP, how we choose to structure things. Also, why we don't do so many transformations, because if we're doing transformations and we're modifying a problem in memory, you'd have to keep track of how to modify those transformations in memory, which is a lot of work. So that's a bit of an explanation of why things are the way they are. So
what modifications can JuMP do now?
Adding constraints, adding variables, column generation, tweaking upper bounds, lower bounds.
Coefficient changes?
We now have coefficient changes, not through JuMP, but through MathProgBase. I think Joachim was responsible for that. So you can change coefficients, but we haven't exposed that through JuMP yet.
Ah. So what's missing? I guess removing variables, but that's...
that's a big issue. Removing constraints. Removing constraints is actually there now, but we haven't exposed that through JuMP either. That's a big question. Why don't we support removing constraints? Well, some of the solvers support removing constraints in memory. Some of them don't support removing constraints in memory. So it's a bit of a question of who keeps track of what when. I think there's definitely a problem that can be solved, but we haven't put in the effort to solve that.
It's also a pain on the JuMP side because we have to keep a mapping between.
Yeah, so it affects how we reference constraints. If we allow removing constraints, then we can't. It's tricky to reference them linearly because you'd have to update all the indices. So it requires rethinking. We haven't put enough effort into to solve the problem, but I think it's a problem that can be solved if someone really wants to. Okay, so what are the three problem classes that we have today? Linear quadratic, this is basically linear expressions, linear constraints, and you can tack on quadratic terms here. Some solvers choose to encode second-order cone problems through the quadratic interface. We support LP hot starts.
Which solver?
Well, Groby, Cplex.
Go to the quadratic?
Yeah, you write down you write it down as a quadratic constraint, and it infers that it's a second-order cone.
If it has a specific structure there.
Yeah. But that's a bit of a hack, but that's how solvers choose to take them.
But the solver interface handles that, or MathPro.
Groby itself handles that. So we pass it as a quadratic constraint to the Groby API.
So if you write a conic problem, SLCB problem in JuMP, how does that translate to MathProgBase?
If you wrote it as in quadratic form, it goes straight through. Mm-hmm. If you wrote it in conic form, we have a layer that is, we have LP-QP to conic wrapper, which transforms an LP-QP solver into a conic solver and does that transformation there. That might change soon, but that is the one kind of transformation that we do allow. So since we have these separate problem classes, we have a few transformations that we can do to turn a conic solver into an LP-QP solver. We can turn an LP-QP solver into a conic solver. It's a bit messy, but it does work. Oh, and conic nonlinear bridge turns a nonlinear solver into a conic solver. So we have some of these transformations set up, but I don't know if that's the final story.
And then the solver interface uses those things too.
Yeah. Okay, we have, so the solvers that kind of fall into this category naturally, what their APIs look like, are Cplex, Groby, CBC, JuliaOpt, MOSIC, kind of. Well, MOSIC supports multiple interfaces, and Skip also falls into this category. So what does JuMP actually do when you write down a model? It collects the expressions using macros. When you call solve, it'll generate the right data structures. JuMP will call load problem, hand off the problem to the solver, call optimize, get the solution back, and give you the solution vector back. So JuMP is doing the least amount of work possible here. The solvers are doing the hard work, and all we're taking care of is generating the right input structures for the solver. Conic form, which we're going to discuss some generalizations to, right now is defined as having a linear objective. You have B minus AX, so B and A are part of, B is a vector, A is a sparse matrix, part of the data structure, and we have some extra data to define what are these cones that we allow the problem that we allow these affine expressions to belong to. And the solvers that fall into this category that kind of take problems naturally in this form, MOSIC, ECOS, SES, CSTP. That's maybe not a complete list. And so as a preview of what we're going to propose, the proposal will be to extend, instead of having a fixed list of cones, right now we have a predefined list of cones that we allow, and they're defined using symbols in MathProgBase. we would like to generalize that to, instead of having a fixed symbol, let it be a Julia object that we pass directly to the solver. That object could indicate membership in some kind of set, and leave it up to the solver to interpret that object and decide what to do with it. We'll have some standardized ones for the existing cones, but this will be a way to, if we just allow, instead of a fixed set of cones, if we allow any Julia object, this becomes a very general format for saying some linear expression belongs to some set. And then what we'd also like to do is tack on quadratic expressions to this, so then you could say quadratic expressions belong to some set, and that covers almost everything, and it covers LP-QP, so then we would merge LP-QP and Conic into all of this. So there's a big restructuring that we're going to discuss later. Nonlinear is very different. It's based on callbacks for derivatives, gradients, Hessians, Jacobians, expression graphs. So this we're not going to touch too much. We're going to leave it. It seems to be working. People seem to be reasonably happy with it. And so a solver that takes in a problem in this form is maybe IPOpt. MOSEC has a convex NLP solver, Nitro, NLOpt. And what JuMP does here is you write down your model in some nonlinear form. JuMP will generate the right callbacks using automatic differentiation to provide the gradient evaluations that the solvers want.
That not touching, does it include AD?
I mean, not touching in the reorganization that I just mentioned. Yep, at the MathProgBase level.
Which now has no idea, basically. Does MathProg know about AD?
No.
Okay, it's for its parent, right?
Yep. There have been some requests for complementarity constraints on top of nonlinear problems, and if we allow to tack on maybe some of these general constraints to the nonlinear form, then we could represent complementarity constraints. So we'll think about that a little bit, but this general form is probably not going to change too much. Callbacks. So I mentioned that we like interacting with solvers while they're running. Chris will talk a bit more about the issues we learned that when we were implementing callbacks in Powerito. We envisioned callbacks to be solver independent, and we chose to only support a callback when it exists in more than one solver. So we started out with lazy constraints that seemed to be a common callback across Cplex, Groby, GLPK. It turned out when we were thinking about it really recently, I don't know if I understand what a lazy constraint callback is anymore, because different solvers may make some guarantees. They may not even tell you how they're using this callback in their algorithm, so it's not clear what is the algorithm that you're implementing when you provide a callback to a solver. That's a bit unclear, so we might think about rolling back the abstraction a little and making it easier to directly access the callbacks for a particular solver. But I think that's slated for discussion on Thursday. I mentioned a bit about the reorganization. I'll skip this because we have time this afternoon. JuMP syntax. So we had that slide at the beginning where the syntax looked very different. In February 2013, we kind of converged to the basics of what it looks like now. We can define some variables, defvar. So defvar stands for defined variable. The name didn't really make too many people happy, so we changed that to just plain variable. And add constraints. We add a constraint. So if you've been following JuMP, the big recent changes, a year ago we got rid of camel case. It didn't really fit in with the Julia ecosystem. We turned some curly bracket into sum parentheses because this is the sum parentheses is a new syntax that was available in Julia 0.5, and that looks nicer than the curly brackets. So defining variables is a surprisingly confusing point. The variable macro has gotten simpler over time to make it harder to do confusing things. So it used to be the case that you could write down variable m x bracket 1 and then have another bracket 1 to n. And what this would do is create a set of n variables and assign it to something called x bracket 1. So if x is an existing list, you could assign the first element of the list x to a set of variables to a list of variables with entries. This kind of got confusing, so we don't allow people to do that anymore. We don't allow multiple variables with the same name. We're kind of converging on a sense of scope, having a model having its own scope, which includes the list of variables. But if you do want to be extensible and kind of tack on a set of variables to a model without affecting the scope of the model, you can use anonymous variables, and those don't have any names that JuMP is aware of. And again, we're trying to remove as much magic as possible from the variable macro. At this point, it's pretty decent explanation to say that what this statement does is what it'll do is check if the variable is defined in the scope of the model. It'll error if it is, and if the variable doesn't already exist, it'll create a local variable called x. It'll create something in the scope of the model called x, and it will give that variable, the base name of the variable will be the string x. So this is basically everything that the variable macro does. So there's been a lot of confusion about what is the scope of these variables, where do the names come from, but hopefully this, yeah.
Are base names totally independent from the lookup name, like symbol x?
Yes. They're just a string attached to the variables, but they're implemented in a lazy way for performance reasons. Yeah.
And does that base name have anything to do with MathProgBase?
No. This is just the base name is the name that you use that will show up when you print out the model, or if you write the problem to a file and you have the writer write the variable names.
What's 1 colon, so bracket 1 colon n?
This defines a collection of n variables with this is the anonymous variable syntax. So it has no name that JuMP is aware of.
But that's not a Julia object.
This is just our syntax for a collection from 1 to n.
And what is
the format for that? Could you do 0 to n?
So anything that you would put in this anything you would put here, but you just don't put the name of the variable there.
Oh yeah, but what are things that you can do?
Index sets.
Hmm?
I'll talk about that next.
Right.
So these variable objects are also interesting. The way we started out is we were inspired by Ample, and we wanted to allow indexing over arbitrary sets. So we wanted to say, well, you can define a set of symbolic things and index your variable over that set of symbolic things, or a range that's not from 1 to n. What we added in JuMP 0.6 is triangular indexing, so you can have a triangular collection of variables. Conditional indexing, you can choose not to define a variable based on a certain condition. And so this leads to potentially confusing situation where you could get different objects back depending on what your index sets are. So if your index sets are from 1 to n, you get a plain Julia array object because there's nothing special to do there. If all the axes are independent, we return a JuMP array object. And it's worth looking at this axis arrays. New axis arrays package could be something we could switch to. If the axes are not independent, so if you have some conditions or if you have some triangular indexing, then we return a JuMP dict, which is basically just a wrapper that translates X, A, B, C to a lookup in a dictionary where it just takes the keys and turns it into a tuple. So that's what we're doing now. There's some room to rethink that. But that's JuMP container. Semi-definite programming. So for semi-definite programming, this required us to think really seriously about vector-based syntax. And what you can do now is you can write vector operations and perform them vector transformations. You can write a matrix of variables times a set of coefficients. And the way that works is just plain operator overloading. So the thing that we said was slow in the beginning that we didn't choose to do. For vectorized operations, it's not too bad if you don't have too many of them because you do them all in chunks at a time. But even if you write vector-based operations inside a macro, it won't be too fancy. It'll fall back to operator overloads for if you have vectors or matrices involved. And I'll skip discussion of symmetry. For nonlinear programming, what JuMP does is it does automatic differentiation. I don't need to talk about that now because I gave a JuliaCon talk last year, so all the details are pretty much there and hasn't changed too much. In the future, we might there's a good chance that we might switch to Jared's reverse diff package to swap out our AD, which is more well documented and possibly more maintainable. I'm probably the only person who understands JuMP's AD. So if we can switch away from that, that'd be great. And there's also some potential for performance gains there. JuMP has a lot of internals for extensions, but they kind of grew organically as someone needed some certain feature to write an extension. So if it wasn't too much work, we threw it into JuMP. The basic thing is we have an extension dictionary object inside of a JuMP model. So if you would like to tack on extra information to a JuMP model, just throw it in the dictionary. We have a solve hook, so you can overwrite solve. Our find expressions are generic, so you can, especially for so jumper for robust optimization, jump chance for chance constraints, it's useful to have affine expressions where the coefficients of the affine expression are affine expressions in different objects. That's useful for modeling. You can reuse JuMP containers to define your own types of objects. We recently generalized the variable syntax, so you can create a collection of things that are not JuMP variables, and added a syntax for set inclusion. So if you would like to override what happens when we say we have kind of a new syntax, hasn't really been used yet, but if you write some affine expression belongs to some object, we have basic support for that. Okay, JuliaOpt. I want to say a bit about JuliaOpt and what I think JuliaOpt is and isn't. We started in October, November 2013 as a, at this time, it was very early in Julia, people were making organizations for let's put all of biology in one organization, one GitHub organization, let's put all of optimization in one GitHub organization, let's put all of statistics in one GitHub organization. So JuliaOpt kind of followed in that pattern. So it was thought about as an umbrella group for Julia-based optimization projects, and I think a good analogy, at least the way I think of it, is like a united federation of open source optimization developers where everyone is just collaborating and doing their best and helping one another. And I don't know, I would say that didn't actually work out as planned. It turns out that people are not motivated to just sit around and help each other all the time on all packages and give unlimited amounts of support and development. So what happened a few months ago is we restructured JuliaOpt a little bit, and thinking that, well, GitHub organizations were designed to, what they were designed to do is facilitate managing permissions and tasks across multiple repositories. So we're going to use it for that, to manage permissions. They were not designed to be a public brand. It's just a GitHub organization with the name JuliaOpt. JuliaOpt, so right now I would say it's organized around collaboration and people who need to work on these packages, people who are working on JuMP, who are working on solver interfaces, and have good reason, motivation to be working together on a package. Well, that's what the JuliaOpt GitHub organization is for. So therefore, the Optum family of packages kind of split off onto its own because there was really not much collaboration happening between the JuMP people and the Optum people, and it didn't seem, on a technical level, there was no need for shared permissions. It was just something that happened to be together for historical reasons. So that leaves open maybe a vacuum for United Federations of open source optimization developers. So if someone would like to launch an organization like that and keep it alive and do peer review of optimization software and quality control and nice support forums, if someone would like to do that, they're welcome to do so. So I'd say JuliaOpt stepped back a little bit from that role, but we're kind of refocusing on the packages in JuliaOpt themselves. And I'm over time, and I didn't put any thoughts on this slide, so maybe I'll keep this for private conversations. But it's open source has been a great choice for JuMP. It's allowed people to use it, contribute back. We've got well, everyone's here because JuMP is open source. You wouldn't be here if it was commercial. So it's been great, I think, to use open source in the most effective way. You have to keep in mind what are people motivated to work on, what are people motivated to spend their time on, and kind of facilitating. Well, what I'm here to do is facilitate everyone achieving some project that you want to work on, because people are here to work on certain projects. You're writing a solver, you're writing a new modeling interface. My role, kind of in one of my roles here for this meetup, is to facilitate and help you work on your projects that you're actually motivated to work on. And I'm not going to ask you to do annoying tasks for JuMP that you don't really care about. If you have some reason to fix a bug in JuMP, that's great, and I'll help you do that. But I'm not going to ask people to do work that they have no motivation to do. And so with that, I'll hand it off to Chris.
Let's take 30 seconds maybe, grab a drink, whatever.